All right, gang. Math 6610, two-way Anova. I'll tell you something. I'm not prepared to put this lecture up, but the beauty of it is well, long story short, I'm going to wing it. I feel like I know this stuff well enough to wing it. I guess time will tell. The beauty of this is if this video fails, you guys will never see it because I'll just trash it and put up another one. So guys, we'll see see what happens here. What we're doing is we're getting into two-way ANOVA, and as you would think about, this is just kind of a way to do two ANOVAs, but in the spirit of not conducting multiple tests for the same motivation that if we have three groups, we wouldn't conduct multiple t-tests. We would conduct an ANOVA to compare group means over three groups, four groups, five groups, anything more than two. The motivation here is pretty much the same thing. So instead of doing two ANOVAs, we kind of imagine starting out with a quantitative variable. And I like to call this layer one. Layer one is a categorical variable. Now, in layer one, all we need here is two groups or more. Now, if we stop there and we have a quantitative variable, and I don't know, think whatever you want to think. Let's think ACT if you'd like, and categorical variable. Let's just think gender, if you like. If we stop right there, we've got a quantitative variable over a categorical variable with two groups only. Guys, we're going to do a t-test there. But if we're conducting a two-way ANOVA, we have a second layer, which is also a categorical variable, which also has two groups or more. All right, so in a sense, what we could do, let's say, for example, this first, and I don't know what we want to talk about down here. Maybe we can talk about race. I have no idea, whatever. Flips your lid there. Flips your lid. That's a new one. I think that's the first time I've ever said that in my life. I don't know where that came from. But anyway, we'll try not to flip any more lids here. We have layer one, layer two. So I forgot where I was headed with this. I got sidetracked with lids. But anyway, if we have a quantitative variable over two layers like this with two categorical variables, we could conduct an ANOVA if we had three groups or more, and a separate ANOVA for three groups or more, and do two ANOVAs. Or in this case, we could do two t-tests. Well, a two-way ANOVA combines all of this and has certain statistical advantages. So guys, a few advantages that I'm going to summarize. I'm not going to write all this out. I consider two-way ANOVA to be more efficient. So I think it's more efficient to I don't know how I want to put this, study two factors at the same time than it would be to study them separately. Another thing important, this reduces our error variance. Now, if you think about our sum of squares, we have our sum of squares of our treatment or sum of squares of our group. And we also have our sum of squares of our error. Easy for you to say. Well, by adding this extra factor in, we're going to reduce the error variance in our model. And guys, I think the most important advantage to a two-way ANOVA is it gives us a way to investigate the interaction. In other words, if we have a two-way ANOVA with factors A and B, which I called layers up here, layer 1, layer 2, factor 1, factor 2, we can investigate the interaction of A cross B. Now that turns out to be important because imagine if we were looking at maybe a final exam score across a particular type, two particular types of instruction across gender. Well, it may be the fact that one particular type of instruction in mathematics works better for females than for males. You know, I'd hate to think that there's any instruction out there that contains gender bias, but I'm just trying to come up with an example if you want to know the truth. So hopefully there are more clever examples than that one. All right, let's go with this. What I want to look at next is let's look at the way the error decomposition breaks down in a two-way ANOVA. So if you want to think about, first of all, we have our sum of squares total, and we can break that into the sum of the following four parts. The sum of squares for factor A, well, it would help if I had two S's, plus the sum of squares for factor B, plus the sum of squares for the interaction, and plus the sum of squares, obviously, for the unexplained variation in our model. When we carry out a test like this, we're going to set up actually three hypotheses. And the first hypothesis is going to be related to just factor A. So we're going to look across, for factor A, we'll have whatever we'll say we have K groups in factor A. Factor B, we'll look at the means for the groups. And let's just call this, let's say we have L groups for factor B. And then for the interaction, we'll have a null hypothesis. And we'll just say that the interaction is not significant. So a good way to look at this is, let's say we have some data, we have a quantitative measurement. And we want to look at this over groups A and B. Well, we can take our measurement, and let's just say that A has two groups and B has two groups. Well, this first null hypothesis is going to compare the equality across the means across groups A1 and A2. This is going to compare the means across B1 and B2. This part right here is going to look at the equality of the group means across the different components of the different layers. So for example, we might find that females with a female professor score better than females with a male professor, and male students with female professors, and so on and so forth. Maybe there's something going on there. I wouldn't see any reason that there would be. Across the board, it may be true for particular professors, but I wouldn't see any reason to think that that's universal. All right. All right, let's see what we can get into now. I've got a data set, and I think I've kind of thought a little bit about this driving in yesterday, how I wanted to actually present this the first day. And I think it's going to be best for us to get hold of a data set. So let me get over here and show you what I've got going on. I got an extremely large data set here. And what we've got is we've got a balanced design. You can see that we've got a large study here, a lot of kids, a lot of students. And we come all the way down, I think we have 800. Yeah, and there's two levels of instruction, dual credit and traditional. Traditional just means that the student was taught on class, on campus, traditional way. And let's say that the other option was to take the course dual credit. And we have males and females. So we're looking at this across gender. And this is actually, the points actually turned out to be, I'm pretty sure, the sum of scores on 2 exams. So I'm pretty sure that's what it was. It was a number of points some way, somehow in the course. So we had consistent grading, consistent exams. Now, so what we've got here, to go back over and take a look at this, what we've got here is we have, the instruction, and we have traditional on class, on campus, and dual credit. And we want to look at that across genders, obviously male and female, okay? Now, the very first thing that we would want to look at here is we would want to focus on our main effects. I want to focus just on traditional and dual credit. So I want to see, carrying out kind of an elaborate glorified t-test, are the mean scores different just across traditional and dual credit? So I'm going to let that be hypothesis number 1. So it's my null hypothesis. So I'm going to test that the mean score, the sum of scores, across traditional as compared to dual credit versus the alternative not equal to dual credit. All right, so that's going to be the first set of hypotheses. The second set of hypotheses are going to look at just over gender. Forget which way they actually took their course. Is there any difference across genders? So guys, you should know now that we're going to test that the mean scores across males and females are equal versus the alternative mean scores across male and female are different. Okay? So guys, this is hypotheses 1 and 2. Now, the other hypothesis is going to hypotheses, I should say, are going to deal with the interaction. So we would say there's no interaction effect between gender and instruction. In the alternative here, there is an interaction. And I'm running out of space here, but just go ahead. There is an interaction between gender and instruction. Okay? So ultimately, gang, what we're going to end up with, we're going to end up with an Anova table that's going to be very similar to the Anova table that we do in a standard Anova. Let me show you the way this is going to fall out. What's going to happen here is we're going to end up with our layers, if you will, and we're going to have a row for factor A, a row for factor B, a row for the interaction, a row for our error, And although R doesn't include a row for the total, we will typically think about that. And I'll explain why in just a second. Now, we're going to have a sum of squares for each one of these, and I'm going to show you how to calculate these. We're going to have the degrees of freedom for each one. We're going to end up with a mean square for each one. We're going to end up with an F statistic for each one. And we're going to end up with a p-value for each one. Now, be really helpful if you could see all that, right? So we're going to calculate an F statistic and a p-value for layer A, an F statistic and a p-value for layer B, and an F statistic and a p-value for our interaction. Now, we don't calculate an F statistic and a p-value for our error term, and the reason is because when we calculate the F statistic for each of these layers, we take the mean square for that layer divided by the mean square for the error term to get our F statistic, and we calculate the p-value based on the degrees of freedom for the layer term, comma, the degrees of freedom for the error. Wouldn't make sense to calculate the F statistic for the error for obvious reasons, okay? Now, the very first thing I want to get into is I want to show you how to make these calculations by hand, okay? Because I think if we just jump into a problem and start, you know, just throw the data in R, you know, do the AOV command, which I'll show you is very, very simple. I don't think you're necessarily going to understand as much about where these values come from as I want you to. Because, you know, in our program, part of, I always feel like I've got kind of a dual mission here with you guys as graduate students, and considering the way that our program was designed. Some people have complained that our program, our master's, doesn't look like other masters, you know, at UK or Ohio State or, you know, wherever. It wasn't built to. Our program was funded early on by the Ohio Board of Regents, who gave us right around $100,000 to start this program, with the intent of credentialing teachers to teach dual credit in the high school. So I feel like I've always got kind of two missions here, not only to teach you some substance mathematically, in this case statistically, but also kind of to prepare you to teach. So if you ever do run into teaching two-way Anova, you'll have a foundation from this class on where the calculations, how the calculations are arrived. So guys, the very first thing I would want to do is I would want to calculate the sum of squares for just factor A. And let's just call this, in this case, gender. Now, something I expect you to know by now is that the sum of squares over gender would be calculated from taking I equal 1 to 2 for the group means, so the group mean minus the grand mean quantity squared times the sample size. Now, let's see how we can take care of that in R. Now, so I'll tell you, part of this, there's a lot going on in this video, or at least I hope there is. I haven't screwed up yet. But there's going to be a lot of how you handle your data in R and do certain things. So you know, keep that in mind. So let's see, up here in Microsoft Excel, I'm going to save this. And I'm going to call it dual credit gender. And I want this as a comma separated value. Save it on my Mac. And I want it saved on my desktop. Now, I usually don't give something a name that long because I just don't. All right, gang, let's bring up R. And I will tell you something. What I do in R here is I typically go up and do script. Yeah, let's not do anything just yet, okay? So guys, I'm going to set my working directory, and I'm going to go get my data. And I'm going to attach my data, and I want to see how the names are entered. So I have all lowercase group, and I have ID. Now, what I want to be able to do here is I want to focus just on gender. So what I need over here, let me get this thing kind of a dual screen presentation. I think that's going to work much more nicely here. All right, so I need to get my information from R. Now, first of all, what I'll do here is I will use tapply, and I want to take my points across gender, and first thing I want to do is get my length, because I need my length right here. Now guys, if I do the length of a variable, that's going to give me my sample size within each group. If I do my length of my data set, that's going to tell me how many variables I have. So let's do this, and I have 400 female and 400 male. So I'm going to have 400 times a quantity plus 400 times a quantity squared. Now, the next thing I need to do is I need to come in and get my my group means. So all I need to do there is just, so here I'm going to have 131.9925, and over here I have 116.9875. Now I need to take that from the group mean. So guys, to do that, I just want to find the mean for all. So it's 124.49. All right, now I'm going to grab my calculator. No, I'm not, because I don't have my calculator. So I'm going to go 400 times 131.9925 minus, I'm just going to put the mean of points there, quantity squared. And I'm going to go 400 times 116.9875 minus the mean of points, also quantity squared. All right, what did we do wrong here, or what did I do wrong? Attempt to apply non-function. Huh, I don't know what's going on here. Well, let's just save some stuff then, if it wants to be complicated like that. Huh, I have no idea why that... Oh, I know what it was. Okay, guys, I see what happened. Let me go back up and get... shoot. All right, let me go back up and get this. This has to be 400 times. 400 times, okay. All right, gang, so my sum of squares here is, let's just call it 45,030. Now, the next thing I want to do is I want to take a look at the sum of squares for factor B, and we'll just call this the sum of squares over our instruction. Now, still we have two groups, so I'm going to call this J equal 1 to 2. of our sample size. We have a balanced design, 400 in each cell. I'm sorry, 200 in each cell. And I want to take same thing here. Now, so what I'm going to do now is I'm going to go up to t-apply, but instead of points across gender, I'm going to do points across group. And I want my length, which we know is 400 in each group, and I want my mean. Now, so what we have here is we have 400 times 139 minus 124.99 squared plus 400 times 109.98 minus 124.99 quantity squared. So I have my sum of squares to calculate here. So I'm going to have 400. I'm not going to make that mistake again. So 139 minus the mean of points, quantity squared, plus 400 times 109.98 minus the mean of points, quantity squared. So guys, we get 168,432 as our sum of squares for the second layer. All right, now guys, at the end of the day, remember we've got our sum of squares for our total. When we're talking about the error decomposition, so our sum of squares for our factor A plus the sum of squares for factor B for this plus the sum of squares for our interaction term and the sum of squares for our error term. Gang, I know that one and I know that one. If I can figure out two of the other ones, then I'm going to be set to go because I can calculate the missing one just using either just a basic operation. Now, next thing I want to look into is called the sum of squares for the total. And the sum of squares for our total, I'm going to see if I can remember the, let's see, I know we take the sum from I equal 1 to A, which A is the number of layers for factor A, from J equal 1 to B, which B is the layers of B, and then we run, let's just call this IJK equal 1 to N, which would be our sample size. So what we're doing here is Y sub IJK minus Y bar. Now, I have no idea why I changed to Y's, because it's the way I remember it is the reason. Now, I want you guys to think about this. What are we actually doing here? If you had a student that asked you, well, that's fine and dandy, you got all sorts of summations going on, but what are we really doing here? Well, notice we don't have a mean here, so we're not looking at any mean. This just tells us that we are looking at each observation. I guess that should be squared, obviously. Each observation. Okay, you might say, well, why? Obviously. Sum of squares, okay? And so we're taking each observation minus the grand mean, and we're squaring it, and we're summing it up, okay? Well, that's going to be super, super, super easy to do with our R. So how do you think we're going to do that? Well, what I'm going to do is I'm just going to create something. I'm just going to call it X. And I am going to take each observation in points minus the mean of points and I'm going to square each one of those. Now we'll come in and take the sum of x, and I get very simple, very quickly, that the sum of squares total is 407,985.9. Okay? Now, the sum of squares for the interaction term is really kind of easy to calculate, but it's not as easy to calculate for the sum of squares error. Actually, it probably is as easy to calculate for the sum of squares error, but I want to point this out because it brings up kind of a unique feature in R that I want to show you about. So still, we're going to have triple summations. Where n is our sample size, and we'll have x ijk minus the mean of ij quantity squared. Now guys, what that notation is telling us to do is we want to sum up each observation and subtract the cell mean. Subtract this from the cell mean. So essentially what we need to do is we need to partition out our data into 4 groups. We're going to have males and females. We're going to have traditional and dual credit. So I'm going to have a mean here, a mean in each one of these, and then each observation in here, you'll come all the way down to x to 200. I want to take each observation, subtract it from the mean, square that, and add them up. Okay? So I want to do that for each one. So it's going to take a little bit of work. Now, how do you get R to do something like this without, just to concentrate on, for example, one group? Well, there's multiple ways that we could do this. First of all, to get the group means here, what I would do is do the t apply over points, but I would list this across group and gender, okay? And then I would come in as my function for mean. Now what that's going to do, that's going to give me my means across each of the groups that we listed. So I know that I have female in campus, has a mean of 148. I know that male in campus has a mean of 130. And I know that dual credit and female over here is, I'm just going to call that 116. And I'm going to call this one 104. So it looks like to me, in terms of the interaction, there seems to be a lot of difference between males taking this course dual credit and females taking the course traditionally. So because there's such a wide difference between that 148 and 104, I'm saying that we're probably going to run into, and I haven't worked this problem, I say we're probably going to run into an interaction here that's statistically significant. I don't know that yet. We've got to let the sum of squares and degrees of freedom and our F calculations and everything take its place. But I'm betting, because of that drastic difference here, that we're probably going to have a statistically significant interaction. Now, gang, let me come in. Let's make this bigger. And so I want to show you how you can come in and actually separate your data out. Now, we got a balanced design telling me that that I have 200 in each group. Female campus has 200, male campus has 200, and so on and so forth. So what I want to do is I want to go back to my data set and see if I can, easy for you to say, see if I can figure out what we got going on, okay? Now I'm writing this down over here some place, if I can find a scratch sheet of paper, and I just want to know where the partitioning out it actually lies. So I have 1 through 200. And let me show you exactly what I am doing here. All right, so I have 1 through 200 that's campus females. And then I have 201 through 400 that's campus males. And then I have 401 through 600 that's dual credit female, and then obviously I have 601 through 800 that's dual credit male. Now what I'm going to do is I'm going to go into R and I'm going to set up some new data frames, because I think that's going to be the easiest way to work this problem, and it's going to be a trick that I want you to be able to do as well. It's very, very handy when you have situations like this. So what I'm going to do is I'm going to come in and create 4 data frames. So I'm going to call my first one CF for campus females. And I want my campus females to be from my data set data. Now, way back here, when I originally named my data set, that's what I have to put right here to implement this feature, implement this command. Now, what ultimately happens here is I have a comma, and this will tell me, the very first entry I have will tell me the rows that I want to select and save as CF, and this will tell me the columns I want to select. Well, what I want to do here is I want to choose the cases 1 through 200 as CF, okay? Now here, if I don't, let me just show you. If I don't do that, it'll give me, well, actually it didn't. I lied. I thought I had to leave a space there. Now the next thing I want to do is I want to call this campus males, and I want to choose my data, and guys, it can't be parentheses. It has to be a bracket. That's not a bracket. What is that called? Yeah, whatever. All right, 201 to 400, and leave our space. The next thing we're going to do is our dual credit female from our data set, and we're going to use 401 up to 600, space, and then we're going to have our dual credit males, and we're going to have our data 601 up to 800. All right, now I have 4 subgroups of my original data set. Now I want to make my first calculation. Let's go back to split screen here. I want to make my first calculation. All right, let's go back. All right, there we go. Sum of squares there is where we are. So I want to make my first calculation according to this. So what am I going to do? I'm going to take each observation in each of the 4 cells, subtract it from the mean of that particular cell, square it up, and get my sum of squares for that group. I'm going to sum all these up and get my total sum of squares for the error. So it should kind of make sense what we're doing here, because we're talking about the error in our model, and we're looking at just how much these individual observations deviate not from the total mean, but how much they deviate within their each cell. And we call that the sum of squares for the error. Now, the first thing I'm going to do over here is I'm going to come in, I'm going to attach CF. Now, it'll say it's masked the data. It just says that it's using variables that have been in a previous data set that have been used. But now you'll see that if I do length points, it's just going to give me 200 because it is just looking at the data in the first 1 to 200 cases. So gang, what I'm going to want to do here, I'm going to set up, I'm going to call it XCF. And this is going to be what? It's going to be my points minus the mean for the points, quantity squared. And then I'm ultimately going to want to take the sum of XCF. So gang, I get for XCF, which that would be, or I'm sorry, the length for, what do we do here? Attached CF. So that would be the on campus for females. So guys, this right here will have a sum of squares of 52,684. Do you think you'll have to calculate a sum of squares for a particular group when you come to campus for your midterm? I promise you. Okay. Now, the next thing I want to do is I want to attach CM. Show some things that are masked. Again, it just means that in previous data frames, we've used the same variables. Okay. Now, I'm going to go up here, and I'm just going to implement that again because it's going to do it for what the data frame that I have open. So 58,192 will be the sum of squares for the males across traditional. All right, guys, let's attach DCF. Let's go up and get the command. So the dual credit female, which is right here, is 407,965.6. And then we want to just attach, what did I call that, guys? DCM. Get the up arrow, get that. We have 31,091, let's call it. All right. Now look at the sum of squares. Where does the most deviation happen? Well, with the biggest sum of squares, this is 58,000. This is 407,000. The females within the dual credit, this has a lot of internal variation. This has a lot of error of the deviations of the observations away from that particular mean. So this and the lowest is the 31, the dual credit for the males. Okay, so let's just keep that in mind. So I want my total sum of squares, and this is for the error, and that's just going to be, see, 58192 and 52684. Yeah. And 407 965.6 and 3109 0.88. All right, gang, so our sum of squares is 549 932.5. That doesn't seem right. In fact, it doesn't seem right at all. Doesn't seem right. All right, 407. 103.